Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. I need to build something and I needed some DC-DC step-down converters. And obviously I thought about the cheapest ones on the market, but I did not knew exactly how good they are. So I decided to buy 5 of the absolute cheapest ones that I can get here in my country and basically put them to the test, perform various tests on them to see how they perform, and basically draw a conclusion at the end if and what I could potentially use. Now in my case I will want to drop down a voltage from 12 to 5 so that I can power a hard drive, but well, these are all, well, I have tested 5 models. 4 of these are adjustable models, so you can adjust the output voltage as you wish. One of these 5 is a fixed voltage, 5 volts on the output. Anyway, I don't know if you will be able to buy these in your country from your local distributors. However, I'm pretty sure that they are available on AliExpress as well, or in any other place like AliExpress, eBay, something like that. So I make this video, you know, in the hope that it will be useful to some of you if you decide to buy something like this as well. The reason why I tested these is because we just cannot trust the description that we find on the online shop where we find them and where we want to buy them from, okay? I have seen this in the past, and I've made a video on this channel as well about 2 very small DC-DC step-down models, converter models, that were not anywhere near their written specifications. So it made sense that I shouldn't expect these ones to actually match their specifications, okay? So I will take them one by one and I will show you my findings, the results of my experiments, and in the end you will draw your own conclusion whether something like this fits your needs or if not. So I will be drawing only a personal conclusion, and other than that you are left to decide for yourself, because overall these boards are not bad, but they are not good enough to be used as they are. And this is my overall conclusion. Anyway, let's get into the details, compare the informations that we get from the website, at least from the website where I bought them, and let's compare them with actual results from actual experiments. So the first model, that's the absolute cheapest model, is based on LM2596 integrated circuit. It says that on the input it accepts from 3 to 40 volts and it costs about 1.4 euros for this entire board, right? So 1.4 euros, that is with VAT included, and with all the taxes included, and this is a first point in which we have to, a first moment in which we have to basically place a question mark, because this cannot be really that cheap. Well, it is, the product is actually that cheap, okay? I actually bought it for 1.4 euro. However, the reason I'm saying we need to put a question mark on it is because if we search for LM2596, just the integrated circuit, okay, we find, and we have to search for the adjustable version, because there are I don't know if you can see, well, the image is rotated, but it can clearly be seen. There's a dash adjust here, which comes from adjust. This LM2596 comes in various variants for various fixed voltages on the output, like 5 or 12 or whatever. And there's also this dash adjust variant that is used for adjustable voltage. And if we search it on two of the biggest distributors, one here in Europe, Temu, we see that just the integrated circuit, the cheapest adjustable version of this integrated circuit, costs about 36 lei, which is about 8 or 9 euros. About 8 euros, $9 or something like that, just the integrated circuit. Okay, if we search it on Mouser, we see that there are a few pieces, well, quite a few pieces in stock. The cheapest, absolute cheapest one is about 13 lei without VAT, so I'm guessing about 16 lei with VAT. That's about 4 euros, somewhere between 3 and 4 euros a piece. So considering just the integrated circuit costs that much, obviously we have to put a question mark on this entire board, whether related to the quality of the board, since this is way cheaper than the integrated circuit himself. Now this leads us to thinking that we could find ourselves in one or of two potential situations. Either one, the happy situation in which this board was manufactured a few years ago in large quantities, back when all of these integrated circuits were a lot cheaper than today, because today we are faced with this stupid semiconductor and artificial semiconductor crisis that has been created, and all the prices have gone up to pretty much every electronic component. But back a few years ago, I imagine this integrated was costing a lot less. So it is possible that this module was built back then, and so now we are buying it with an old price, which is of course good for us. And hopefully this is the situation, because in this situation we would have a genuine integrated circuit. The second option that could potentially be true would be that, well, no, this does not have to do with the price of the integrated circuit itself. It's just that this integrated circuit is actually a cheap replica of an actual original. Okay, so if we take a look at the picture, we see National Semiconductor logo on the integrated circuit. If this is genuine, then this is truly a National Semiconductor component. However, it is possible that this is not, that this is just a replica, and therefore we are having a, how you guys say in English, a cheap knockoff. Now, personally, I don't care. You know, I don't care if a component is a fake, a replica, or it's an original, provided that it performs similarly or identically with the original. I really don't care who manufactured it, at what cost, and you know, I personally don't care about these details. However, it's important that we are aware of such situations and such details. Okay, now moving on, what do we find about this board? Well, it says that we can have from 3 to 40 volts on the input. It says that we could have from 1.5 to 38 volts on the output, which we will see it's not true. It says that we can have a 3 amp output maximum current, an output, a maximum efficiency 92%, emphasis on maximum, and a ripple voltage of 30 millivolts. They also give us the switching frequency, but personally I don't care about that. Now, let's see in practice if these are true, which ones and which ones are false. So, I have tested all of these boards in some fixed conditions so that we can easily compare between them. I have set all of their voltage, all of their output voltage to 5 volts, okay? First of all, because there is a model that I will show you in a moment that has a fixed output voltage of 5 volts because it has an USB connector, and of course we cannot risk connecting anything on USB that receives more than 5 volts, because then we could potentially burn it. So and also the second reason is because I need 5 volts in my project. I need to drop down from 12 to 5 volts. So I set all of these boards output to 5 volts. And I have tested, I have created 2 sets of tests with 12 volts on the input and then with 27 volts on the input. And I've chosen for each of these values, of these voltages, I've chosen a few fixed currents. I have drawn them with my electronic load, and at each current I took some measurements about the input current and I calculated the efficiency in percentages here. I also had I did my best to measure the temperature of the integrated circuit with a thermocouple and a separate multimeter, okay? And with an oscilloscope, I was visualizing the output waveform to determine the ripple voltage, okay? So these tests were conducted like this for all of these boards, so we can easily compare between them. So, first things first, the first thing that we need to be aware of, and I think it might even be possible, yeah, even on the, even in one of these images on the online shop, we can see, barely, but we can see that the output capacitor is rated for 35 volts. This tells us immediately that we cannot possibly go up to 38 volts on the output because the output capacitor is limiting us. So this is an important detail, okay? And you can see here a better picture of it. This is an important detail that we need to take care of. We cannot use more than 30 volts on the output because of this 35 volts output capacitor. It should have been like the input capacitor, which can go up to 50 volts, but for some stupid reason they decided not to use a better capacitor. Anyway, so this is the first information that is false on the on the description of of this product. Now, a small parenthesis, because I forgot to mention, I'm in no way affiliated with any of these companies that I'm presenting to you. And also, I'm not trying to bash anyone or to critique anyone in particular. I'm just trying to analyze the products and show their performance to you. Okay, so we are looking at products here, not companies, not the people behind them. Okay, so this detail is obviously false. We cannot go up to 38 volts, but 30 volts maximum. Also, the efficiency, they say maximum efficiency of 92%. Well, it is partially true in the sense that yes, I've achieved a 92-93% efficiency, but only when I had 20 volts, 27 volts input, 5 volts output, like I said, and very small current, 100 milliamps. The more the current increases on the output, the more the efficiency drops. Also, when I had 12 volts on the input, the maximum efficiency was 83% and it dropped from there. Okay, so that 92% efficiency is not true in all conditions, but only in very specific conditions. We can get down to 57% efficiency when we have 2 amps on the output. Also, the temperature, Well, pretty much all of these boards mentioned that for higher currents we should apply forced cooling on the integrated circuits, meaning we should put a small radiator on them. I didn't. I performed all of these tests without a radiator, so that I performed this test uniformly, okay, in a uniform manner. So the temperature that I measured with a thermocouple started to rise from very small currents up to the higher currents. I've measured for 12 volts input, I've measured 90 degrees, around 90 degrees for 1.5 amps on the output. When I went up to 2 amps, temperature went to 100 degrees, of course Celsius, not Fahrenheit. I haven't mentioned, but you know, it's by default Celsius. 100 degrees, and it was climbing even higher, so I stopped the experiment at 2 amps at that temperature. So this particular model can be used without a heatsink, without a radiator, up to about 1.5 amps of output current. Okay, when I had 27 volts on the input, I had only about 80 degrees Celsius for 1.5 amps, and yeah, I stopped there because at 2 amps I would have gone up to 100. Of course, we can have more amperage, we can go up to 3 amps as specified, however we need forced cooling. Now, in terms of the ripple voltage, it is nowhere near the indicated 30 millivolts. First of all, ripple voltage is not constant, it actually varies based on all of these factors: input voltage, output current, and yeah, it's a lot worse than what is written in there. Okay, this was the main reason actually why I wanted to perform these tests, in order to see the ripple voltage and in order to see if I can use these voltages directly where I want them. So when I have 12 volts input, 5 volts output, 100 milliamps on the output, ripple voltage was about 80 millivolts, and it climbed up to half a volt for 1 amp or 1.5 amps, and then it started to shrink a little bit when I got to higher currents. Similarly, when I had 27 volts on the input ripple was 140 millivolts for 100 milliamps, and it climbed up to 550 millivolts for 1.5 amps, and the maximum would have, I suspect the maximum would have been around 2 amps or so. So as we can see, the ripple voltage is significant, and it makes it so that these boards cannot be easily used in any project, because some projects have a problem when you have plus minus 250 millivolts. Okay, so this ripple voltage is peak-to-peak voltage. I will show you the waveforms towards the end of the video for all of these boards. Okay, so this was the first board. Now let's move to the second board, which is basically identical with the first board, except it's just slightly more expensive. They used semi-D capacitors on the input and output instead of just through-hole capacitors. And is this particular model here, which we see that it's, well, identical but with semi-D at the end. Okay, and it's 1.6 instead of 1.4 euros. We see that the specifications are a bit closer to reality. Maximum output voltage 33 volts. Well, yes, if we have 35 volt capacitor, then 33 volts is a lot better than 38, which is completely impossible. I would say that we still should be within 30 volts and not go above. We should give that capacitor 5 volts error margin. Okay, output current 3 amp maximum, efficiency 92%, ripple 30 millivolts, just like in the previous model. Well, since in the essence, there is no difference between this board and this board except for the capacitors. I expected, and I also found that there are no significant differences between these two models. Of course, the capacitors do have an impact on a slight impact on the efficiency, and but very small, and a somewhat bigger impact on the ripple voltage. Okay, so for this model, again, the efficiency can be 90 something% efficiency can be obtained only in particular situations: high voltage on the input, small current on the output. Other than that, the efficiency drops, and it drops quite a lot. As we can see, at 12 volts input, the maximum efficiency is 83%. It drops down to 60% at 3 amps of output current. Okay, it seems that overall this board was doing better with cooling down, because I could have 2 amps from 12 volts input. I could have 2 amps on the output, and the temperature would not reach 100. It would be around 80 degrees, relatively constant, again without a cooling radiator. Whereas in the first model at 2 amps, I reached 100 degrees. I reached 100 degrees here only when I went up to 3 amps. Okay, and this seems to be true for both 12 volts input and 27 volts input. By the way, in case you're wondering why 27 volts, that was the maximum output voltage that my lab power supply was able to provide. Okay, so that's why I chose 27, because I couldn't go higher. Ripple voltage is in some cases worse than on the first version with THT capacitors. 210 millivolts at 100 milliamps, 12 volts input, or even 280 millivolts at 27 volts input, also 100 milliamps. It went, for the 12 volts input, it went up to 600 millivolts peak to peak for 1 amp, and then it started to go down a bit as I increased the current. When I tested with 27 volts on the input, the ripple voltage kept going up and reached a maximum of almost 1 volt at 3 amps of current, output current. Okay, which is quite a lot, yeah, and like I said, the only difference is that these capacitors are semi-dev versions, whereas these capacitors are through-hole versions. Other than that, the circuit is identical. Okay, now moving on to the third type of board, this very small board with an USB connector, and a very small chip that does pretty much everything. As far as I can tell, this has both the control and the switching element inside. It costs 1.6 euros, just like the previous board. And since they put an USB connector, they had to have a fixed output voltage of 5 volts. It says that it is capable of 3 amps, it is capable of 3 amps output current and up to 24 volts input voltage, both of them being wrong. They say nothing about efficiency or ripple voltage, which at least it's better that they don't say anything. Well, I managed to burn this this board. So first of all, I performed tests with 12 volts input, and I've seen no significant problems there. The efficiency is overall higher than for those other boards, where we had down to 57% efficiency in some cases. No, here we have a minimum of 80% and a maximum of 91-ish% efficiency, which is good, it's not bad. Also, the ripple voltage is significantly lower than in the other boards. It starts at 40 millivolts peak to peak for 100 and 500 milliamps output current, and it goes up to 350 millivolts for 1.5 amps. That's definitely a bit better than having 1 volt at 3 amps in this case, which is ridiculous. Anyway, however, to get back to the specified characteristics, there are two things that are completely false in here. Output maximum current 3 amps. No, it is not possible. When I had 12 volts input, 5 volts output, and 2 amps on the output, I had about 80 degrees Celsius, the temperature of the chip. Now, for the most part, I was unable to actually measure temperatures reliably because this chip is so goddamn small that my thermocouple is literally half the size of this chip. I wasn't able to fix the thermocouple onto the body of the chip, and therefore I wasn't able to have constant measurements of the temperature. But when I started drawing higher currents, I placed with my hand the thermocouple on the chip, and I saw what temperature my multimeter showed. But keep in mind that when we are doing so, and when we are trying to measure the temperature of a very small component, the thermocouple himself, by making physical connection with that component, is taking away heat from that component and acting like a small radiator. So I'm pretty sure that my thermocouple, while I was holding it with my hand, was actually helping this chip cool down, so that these temperatures might actually be 10 degrees or 20 degrees higher than what I was able to measure. So it is possible that at 1.5 amps of output current we had about 80 degrees, and at 2 amps we had about 100 degrees. Okay, because again, it's impossible to accurately measure the temperature on this extremely small chip unless we have something fancy, which I don't. So if we have dangerously high temperatures at only 2 amps, it is pretty clear that we cannot go up to 3 amps no matter what. That's impossible. So that specification of 3 amps maximum current is false. Okay, I would say that we should not go above 1.5 amps no matter what. Also, this basically this board is impossible to be cooled down forcibly by using a radiator, because since this chip is so small and it has all sorts of other components immediately around it, we really cannot fix we really cannot attach a radiator on the body of this chip. So this chip must work by itself, cooling himself down. That means that we cannot go above 1.5 amps no matter what, or we risk burning it. Okay, the second false information here, maximum input voltage 24 volts. No, completely false. When I applied 23.5 volts on the input to stay within 24 volts, my board burned. Literally, it started smoking and it burned. The output voltage dropped down to 0.5 volt instead of 5. It made a short circuit on my lab power supply, and that happened even without having a load on the output. Okay, so yeah, so this board cannot under any circumstances go to up to 24 volts. I don't know what is the maximum voltage. I would need to have yet another board, which I don't, and perform this test again and gradually increase the input voltage and monitor the output. I will not do so because it doesn't make sense. So if you decide to buy something like this, you know, bear in mind that these are very serious limitations that you need to take care of, and not trust the specifications that you are being told. Other than that, yeah, the efficiency is pretty good. The ripple voltage is definitely better than in the other versions, in the other models. So yeah, it has both pros and cons. Now let's move on to the fourth version, which costs 2.6 euros. It says that it uses the high voltage version of LEME 2596. Very oddly, they did use a higher voltage capacitor here, 35 volts. No, sorry, no, they used also 35 volts capacitor on the output, but they wrote maximum output voltage 26 volts. Well, no, we can actually go up to 30 volts. You know, I mean, the rest of the circuit doesn't prevent us. Only the output capacitor prevents us from going above. But yeah, we can definitely go up to 30, not just 26 volts. Anyway, the high voltage part of this means just that we can go up to 42 volts on the input. As far as the integrated circuit is concerned, but also as far as the capacitor is concerned, it's 63 volts on the input, so it is good enough. Again, they say 3 amps output current, maximum 92% efficiency. They don't say anything about the ripple. So, okay, so this is what I found. Since it's the same chip as in the first two models, there are no huge differences. You know, in terms of efficiency, efficiency drops down from 93% when we have relatively high voltage on the input down to about 67% ish. When we have lower voltage on the input, the efficiency starts at some lower value, 83%, drops down to 61%. Ripple voltage starts at around 180 millivolts for very small currents and goes up depending on the input voltage. For 12 volts, we had 500 millivolts ripple voltage at 1.5 amps. So it was climbing up from 180 millivolts to 500, and then going down if we kept increasing the output current. Similarly, for the higher voltage input, the ripple voltage kept going up from 180 all the way to 560 millivolts at 3 amps. Also, this board seems to be good enough to work with 2 amps without extra cooling. It reached only 80 degrees Celsius. So yeah, overall it's similar with the semi-dev version. Okay, and similar but a bit better than the first version that we tried. Again, the output capacitor being 35 volts limits our maximum voltage that we can set. But yeah, overall these results were basically something to be expected. And now moving on to the last version, the last model that I've tried. It costs 3.4 euros. It uses XL4015, so a completely different integrated circuit. It says that it can go up to 5 amps. Sadly, I did not have the necessary equipment to test it up to 5 amps, only up to 3.8. Input from 4 to 38 volts, which is true because we have 50 volt capacitors both on the input and the output. Output voltage up to 36 volts, adjustable, right? And it also tells us something about the output power, maximum output power, and as well as if we go maximum 75 watts output power. So we have to take care of what voltage we are setting on the output and what current do we have, because not all combinations are within 75 volts. Of course, there are combinations that are way above 75. And for more than 50 watts of power, we need to use a forced cooling. However, the nice thing is that, as we can see in the picture, as in the reality, they put on the package, they give you a small radiator that you can glue on top of this IC to cool it down, and you don't have to bother buying an extra radiator, you know, just for this purpose. They just give it to you. They say maximum efficiency 96%, which is, yeah, partially true. So let's see how this went. We have 93% efficiency, again at higher voltage on the input, lower current on the output. And as a reminder, we kept having 5 volts on the output on all of these tests. And then from 93%, the efficiency went down to 75. However, overall, it seems to do a much better job in terms of efficiency than the other boards using the other chips. 75% for 3.85 amps at 27 volts input. For 12 volts input, we had lower efficiencies by about 10%. You know, 83% best, almost best efficiency. It seemed to go up a bit at half an amp, and then it started to go down to 65% at 3.85 amps. This was the maximum current that I could draw with my equipment. I wanted to go up to 4 or maybe even 5. I just couldn't. Anyhow, the temperatures were pretty good. Now, bear in mind that we should mentally add 10 or 20 degrees here. More because I have a suspicion that my thermocouple was not making very good physical contact with the chip. However, the temperatures are relatively close to the reality, and it's clear that this chip is doing much better on an electrical level, because it has much fewer losses, which generate much smaller temperature increase. Okay, we have I've experienced 45 degrees Celsius, which is still relatively cool chip, at 3 amps of output current, 12 volts on the input, and about 40 degrees at 2 amps at 27 volts on the input. So we can definitely use this without forced cooling for quite a high current. Okay, now maybe this wasn't 45 and it was more like 65, because again my thermocouple wasn't doing a very good physical connection, but still it's not 80, it's not 100 degrees, so this is definitely doing a lot better in this regard. Also, in terms of the ripple voltage, it's kind of like the other versions that the other boards that I've presented so far. It starts at around 120 millivolts and goes up depending on the case. For 12 volts input, it went up to 300 millivolts ripple voltage peak to peak for 1.5 amps. And then as I increased the current, the ripple for some reason started going down. Similarly, for the 27 volts input, ripple went up from 120 to 400 millivolts for 3 amps. And then when I increased the current, it seemed to go down a bit. So it's still relatively high, I would say. I mean, I don't know, it still looks a bit too high for me, but it's definitely better than the other options, the other boards that I've tested. Okay. Yeah, so these are my results. In case you decide to buy something like these, now you know. I will show you quickly. I will go through each of them and I will show you quickly waveforms of the ripple so that you have a better picture of what I mentioned earlier. So for this 1.4 euro model, okay, we have this ripple at 12 volts on the input, 5 on the output, no current being drawn whatsoever. This at 100 milliamps, this at 500 milliamps, this at 1 amp, 1.5 amps, 2 amps, and then I switch to 27 volts on the input with no current being drawn on the output. We have occasional spikes like these. For 100 milliamps of output current, we have a ripple that looks like this. 500 milliamps, 1 amp, 1.5 amps, and that's pretty much it. Whenever I'm showing you this, please take a look here down in the bottom left corner at how many volts per division we have, so that you can assess, you know, how big are these waveforms. Occasionally you might take a look here as well, because sometimes I left the measurements on the screen, but some other times I forgot. Anyhow, moving on to the second version, which is just pretty much the first version but with semi-D capacitors. We have these results. So 12 volts on the input, no current on the output whatsoever. 100 milliamps, 500 milliamps, 1 amp, 1.5 amps, 2 amps, 3 amps. Then I switched to 27 volts on the input. Again, on the output we kept having 5 volts, 100 milliamps of current drawn, 500 milliamps, 1 amp, 1.5 amps, 2 amps, 3 amps. Okay, for this board with USB connector, like I said, I was only able to perform a test with 12 volts on the input, because then at 23 something volts I burned it, in spite of it claiming to go up to 24 volts. So yeah, 12 volts on the input, no current whatsoever. This is the ripple. 100 milliamps, 500 milliamps, 1 amp, 1.5 amps, 2 amps of current. Okay. Fourth version with a high voltage, LEME 2596. We have 12 volts, no amp, 100 milliamps, 500 milliamps, 1 amp, 1.5 amp, 2 amps, 3 amps, and then with 27 volts on the input, no current, we see some spikes. 100 milliamps, 500, 1 amp, 1.5 amps, 2 amps, 3 amps, and that's it. Now the last version with the last converter with XL4015. 12 volts on the input, no current whatsoever. We see some occasional sharp spikes. 100 milliamps, 500, 1 amp, 1.5, 2 amps, 3 amps, 3.85 amps. And then with 27 volts on the input, no current being drawn on the output. 100 milliamps, 500, 1 amp, 1.5, 2 amps, 3 amps, 3.85 amps. And that's pretty much it. Okay, so I hope this is useful for you. I hope that now when you will purchase these kinds of products, you will do so better informed. And now you know, before buying them, if they are good enough for your project, if you will need to use some extra circuitry to perform perhaps a linear regulation after the DC-DC converter, or whatever it's in your whatever your case may be. Now you know if you can use these really cheap DC-DC converters or not. So thanks a lot for watching. Please hit the like and subscribe button if you want. If you have enjoyed this video, I am coming back with more, so make sure that you stay tuned. Also, if you enjoy my work here, please consider supporting my work on Patreon. There's a link in the description. By helping me financially buy more components and devices, I can study faster, and I can come here on YouTube and show you my results as well, so that you don't have to bother with your own process of research and experiments and so on, so that you can learn faster and easier. Thanks a lot for watching, and I will see you next time. Bye bye.